there's a velocity of mu there. There's no torque. But remember, for something to rotate, it can still rotate without a torque. What that was basically suggesting to us over here was that since the central force is directed in the same direction as r, and this is a position vector which is pointing to, in some arbitrary space, the reduced mass, that since r and the central force are in the same line, they have 0 degrees between them, that by definition there's no external torque. But there's still an angular momentum, and angular momentum means if it has a non-zero value, then it has to be rotating. So all this is saying is there's no external force, not that it's not rotating. Okay, so this gets kind of messy for us. So let's reduce this, or change it rather. And we're going to change it basically through this relationship. So using this relationship here, in which we found the magnitude of the angular momentum, which is constant, it's a constant of motion. And if it's a constant of motion, then that's something that we are more able and better to use, because that's something that's much easier to actually calculate, especially in a laboratory situation. I'm going to rewrite that. And I'll write that by saying that omega is equal to L divided by mu r squared. And thus, since I have an omega squared here, that says omega squared is L squared over mu squared r to the 4th. And now what I'm going to do is I'm just going to input that into this equation. So here I have E is 1/2, let me now say mu Vr squared plus 1/2 mu r squared, and now let me put this value in. And that value is L squared over mu squared r to the 4th. Now notice what we have here. I have a mu up in the numerator. I have a mu squared here, so that kills one of them. I have an r squared in the numerator. I have an r to the 4th, so that kills 2 of them. I still have, I didn't write it here, the energy is plus the potential energy due to the central force. And now rewriting this in this term, I have the energy E is 1/2 mu Vr squared, so that's a translational, plus here, let me see how I want to write it, 1/2 L squared mu r squared, that's the rotational, plus the potential energy. And here we have it in terms of a constant of motion, L. Now, this of course is acceptable, but typically you would see this written in a different way. You would see in particular that this equation is usually written as E is going to be equivalent to the kinetic energy plus the effective potential energy. To put it back to the general idea of energy conservation. And in doing this, we would say that the potential energy, the effective potential energy, is going to be this term, 1/2 L squared over mu r squared, plus the true potential energy due to the central force. Now in the end, we're just going to need all of these values, but this is how you basically represent it. That once again, you go back to the simple idea that energy is kinetic energy plus potential energy. But here the potential energy term has something added to it. It has this term. And this term has a very special name. This term is called the centrifugal potential energy, or the centrifugal barrier. Centrifugal because it deals with rotation. And thus, what this is telling us is that the actual rotation of an object, or revolution of an object, such as the Earth around the Sun, is going to add a component to the potential energy equation. Now in doing that, we can now understand very shortly why I mentioned previously that if you recall for escape velocity, I wrote escape velocity basically by saying when the kinetic energy 1/2 mv squared, just by saying very simply, I throw something straight up, minus the potential energy, so minus gm1 m2 over r is equal to 0. And then you set them equal to each other. And the basic idea for that is any object that can't make it into space, so such as me, I didn't have enough kinetic energy, so I came back down. I'm bound. And by being bound, that means the total energy was negative. But unbound systems have total positive energy, meaning their kinetic energy is greater than the potential energy in terms of magnitude. We can now clearly see that with this added term. So let me first write, let me say explicitly, now we're going to gravity. So the potential energy term is just going to be negative g m1 m2 over r. Thus the effective term, if we're going to write that, is just going to be 1/2 L squared over mu r squared minus this term. So it's going to be a positive term minus another term, so a positive and negative term. And if we do this now, let's create a general graph. So let this y-axis represent energy. Let this x-axis here represent distance, r. And now what we can see here is two different regions. So just looking at the potential energy of this, because remember the kinetic energy is just 1/2 mvr squared, so that doesn't really matter right now. But just looking at the potential energy right now, the potential energy has two terms. One of these terms is just a constant value, 1/2 L squared over mu squared, and it's divided by 1 over r squared. If we map any general function that's 1 over r squared, it's going to rapidly decay like this. So this is basically our 1 over r squared term. The potential energy due to the central force, in this case gravity, is 1 over r. Now 1 over r in terms of magnitude does drop, but it doesn't drop as quickly as 1 over r squared. And it's negative. So if we look at this one, it's going to appear like this in our graph. So this is going to be our 1 over r term. If we combine them, notice that when r is about 0, at very small values of r, this 1 over r squared dominates, because 1 over a very small number is much greater squared than it is 1 over just that small number by itself. And it's positive. So at small values of r, so for r about 0, the centrifugal term is going to dominate, just in terms of magnitude. As r goes to infinity and gets much bigger, then the potential energy term is going to dominate, because that's 1 over r. And one of them is positive and one of them is negative. So if we combine both of these to draw a graph of just the effective potential energy, it would look something like this. And so this here represents the effective potential energy. And in this, Newton realized a couple of things. That this is broken up in between a basic region of where total energy is positive, and over here where total energy is negative. Getting back to this value here, this being our total energy. If the total energy is positive, that means the kinetic energy is greater in magnitude than the effective potential energy. And thus, if that is the case, then this area is known as being unbound. If the kinetic energy is smaller in magnitude than the effective potential energy, then the energy is less than 0, and thus this is an area that's being bound. Now we can see 4 general regions. One is, let's say that each line represents a constant line of energy. right here. In this case, energy is equal to, say, some minimum energy. Here, let's just say E is less than 0 as our general idea. Our third one being on the R axis, so let me just do a dotted line here. So in this case, E equals 0. And then a third one where E is greater than 0. Now this is sort of known as an area that's called a potential well. And in any field of physics or engineering that you will encounter, if you have a graph that makes this sort of dip, then this region is a bound region. And things can be bound to whatever force law you're describing. Think of it as an actual valley. And let's say you're rolling a ball in this valley, say starting here. Well, just due to potential energy to kinetic energy, it's going to be stuck there, so it's bound. Just as a planet is bound in orbit. Or if this was electromagnetism, this could represent the energy of an electron bound in an orbit to an atom. So with this, Newton, and the next part goes well beyond the actual scope of the mathematical scope of this class, so let me just define for you. What Newton found was that if the total energy is this minimum value, then you would have a circular orbit. If the energy was just less than 0, but not this minimum value, then you're going to have an elliptical orbit. Now before I get to the unbound parts, these two bound. Something else that goes beyond the scope of this class is the idea of stability. Consider for a moment a ball in a valley and a ball on top of a hill. If you slightly perturb them, so move them, let's say this ball in a valley, I slightly move it, it's going to oscillate back here and let's say due to friction eventually comes back to stop. This is an area of stability. However here, if I leave it there forever, it's going to stay there, but if I just give it a little push, either way, it's going to fall down and not be in the same position. This is unstable. And if we include that aspect, what Newton concludes is that a circular orbit is highly unstable. And because there are always other objects in the universe and other planets pushing and pulling at everything, anything that would initially be in a perfect circular orbit would almost immediately decay out of that and go to an elliptical orbit. But elliptical orbits are highly stable. So that's where we get Kepler's first law. All planetary orbits are ellipses because that's the only way you can have a bound orbit. And you only have that bound orbit if the kinetic energy is smaller in magnitude than the effective potential energy. Not just the potential energy, but the effective potential energy, where you have to deal with this term, which is our centrifugal term. The centrifugal barrier, or centrifugal potential energy. With that in mind, if E equals 0, this is a parabolic orbit. Now remember, a parabola basically looks like this. So if you had the sun here and some object in the outer part of our solar system get kicked in, it would just come in, zip around, and come back to a different starting location. Meaning it's not bound. There it does not make a complete orbit. Or if it's greater than 0, it has a hyperbolic orbit. Which means in this case, it comes in from the outer parts, slingshots around, and gets ejected completely from our solar system. Back in the time of Kepler and Newton, what Kepler was able to observe that all planetary orbits are ellipses and not circles, Newton proved and showed us why all moons have elliptical orbits around their planets, why all planets have elliptical orbits around the sun. And he proved that with fundamental physics. What he could not prove at that time via observation was a parabolic or hyperbolic orbit, because objects that are actually doing that, it's happening all the time, are so tiny that we can't observe them. But let me just make one point about the hyperbolic orbit. That is exactly what NASA does when it wants to send probes to the farther part parts of our solar system. So it may seem as if we want to go to Pluto or Jupiter or any of the outer planets, that we should just go directly there, say a straight line. But we don't. We go to the inner part of the solar system, Venus. And we do that because we induce the probe to undergo a hyperbolic orbit around Venus. And by doing that, it gains energy, gravitational energy, from that planet and basically slingshots around it. So it accelerates around it so that it gets ejected from the planet Venus with a faster velocity than it came with. And that's what basically saves us on fuel. Not fuel costs, but the biggest problem in sending a probe into space is actually just getting into Earth's orbit. If you need more fuel, it weighs more, which means you need a heavier rocket, or you need some ability to construct it in space, which we lack both of them. So to overcome those engineering difficulties, you give it less fuel so that it actually couldn't make it to its location, but it could make it to another location. Say Venus, slingshots around, gets ejected from Venus's planetary system, and goes to the outer reaches of our solar system. And that's all because at that point the total energy, the kinetic energy, is greater than the effective potential energy, and energy is greater than zero. And thus Newton here is able to physically describe for us both of Kepler's first and second empirical laws. He shows us why it is through his central force motion. I'm going to take you for a couple of minutes to just do a little bit of derivation and quote the results for Kepler's third law. But before that, is there questions about this?
How does it apply to like subatomic particles with an electron cloud? The orbital.
Same general idea.
It doesn't really orbit in a circle or an ellipse. Like they say it's kind of like a cloud and it's random. So how does that work exactly?
Well, to get to higher levels, you have to use the Schrödinger equation for quantum mechanics. But that's why we generally, and in any chemistry class, they're going to first teach you the hydrogen atom. Because the hydrogen atom is the simplest atom. Has one proton and one electron, very similar to that. And in that case, the potential energy is going to be negative K Q1, Q2 over R, where Q is just the charges of the electron and proton. They're both the same in magnitude. R is going to be how far away it is, so that's usually for an electron. Negative K E squared over A, which is the Bohr radius. That's the distance an electron typically is. And in that case, just with a single particle, this is its potential energy, and it's still, because it's revolving around the proton, has a centrifugal term. For the other ones, even if you get to helium, which is the second simplest atom, it becomes much more complicated because then you have to deal with angular momentum in a much more sophisticated way, because not only are you going to have the electron and electron repulsing each other, you're going to have what's known as screening effects. Say, for example, both the marker in this water bottle represents an electron and I'm a positive nucleus. Well, this electron, because it's farther, is going to feel less of the positive charge because this one is screening it. So it becomes, I'm not going to say infinitely more complicated, but dramatically more complicated once you get beyond it. But for just hydrogen, this is the simple term. And once you deal with angular momentum in a different way, it all basically falls into this. But it requires quantum mechanics to fully understand helium. But just for hydrogen, you could do this.
So does the orbit of like a comet work the same way? There's like another massive object on the other end which circles around?
No, a comet is a highly elliptical orbit. So if this is the sun here, a comet to an extreme basically looks like this. It does make a complete orbit. However, its eccentricity, how elliptical it is gigantic. So that's why it spends most of its existence in the outer parts of the solar system and only briefly comes to the inner part. That's why, for example, Halley's Comet has an orbital period that's 76 years, and others are even greater than that. But it is an elliptical orbit.
When a probe is coming like to Venus, you said, and it gets caught in the gravitational pull,
Mm-hmm.
and isn't it in a bound system at that point? How can it leave?
Because it came in with a more kinetic energy.
What if it didn't lose that kinetic energy?
Well, notice here, the effective potential energy. It has a positive term, which represents positive total energy, and a negative term, the gravitational counterpart. The point about a hyperbolic orbit, and that's why I tried to show it here in blue, is that it comes much closer. Because it comes much closer, 1 over r squared dominates over 1 over r. And that's because as r goes to 0, this number gets higher at a faster rate than this number does. This positive number overwhelms this negative number, and that's what's known as the centrifugal barrier. You get close enough to an object with enough initial kinetic energy, this term dominates, and thus the potential energy, it now boosts the total energy, and it just gets faster.
So they have to make sure it gets like very close to the planet.
Yeah. That's why it's pre-programmed to actually undergo that type of orbit.
So is that why like the moon is closer to a certain time of the month because it's electrical?
Yeah. By the way, that has nothing to do with full moon or anything like that. So when they talk about Superstorm Sandy from last year, and they say all these different events led to this perfect storm, and one of them they say is a full moon. The full moon does not necessarily mean, it happened to be in that case, but it does not necessarily mean that the moon is closer to the Earth. So if anybody says that, you just don't slap them, but slap them across the face and say, it does not mean that. Being a full moon wasn't that important. It just happened to be that it was a full moon and closer. But there are several times when it's a full moon and the moon is at farthest approach as well. So it has nothing to do with the actual relative distance between the moon and the Earth. Okay. Okay, so now let's deal a little bit with Kepler's third law, though I am going to jump at one point and just quote the results. And that's because the amount of mathematics becomes extremely difficult. Not that it's many lines of algebra, but it basically, the only way to fully solve it is with calculus. And that's why your textbook in chapter 12 just quotes the result rather than shows you any type of derivation. But I want to show you just a little bit. So let's start with, once again, the constant magnitude of the angular momentum is mu r squared omega. But let me rewrite omega by the definition of omega. Let me rewrite this as mu r squared, the change in theta over the change in time. Remember, that's what omega was, really. Omega is the total angular displacement per time. That was the definition of it. Just like velocity is the change in displacement over time. Remember, when we go to rotational, displacement x becomes angular displacement omega. Linear velocity becomes rotational velocity. So this is just the definition of it. Now let me cross multiply. So let me put time on the other side. So if I do that and divide by, so let me first say this, I'm going to divide both sides by 1/2. If I do that, then I'm not changing the actual value because both sides are unequal. If I just multiply them both by 1/2, I haven't changed anything. And I am going to divide both sides by mu over change in time. So if I do that, what I end up getting is on the left-hand side, the angular momentum L over 2 mu times the change in time is equal to 1/2 r squared, the change in angular displacement. Okay. The most important thing here is that this is a very tiny element, so a very small, infinitesimally small element of area. This is a small element of time. And for those of you who have taken calculus before, you realize that if you have a small area of something, on the left-hand side time, and on the right-hand side area, you can integrate them. Which, for those of you who don't know that, let me best to say that what I'm suggesting here is that let's take some part of its circular, near circular orbit. Here's R. Here's a new vector. This is the change in theta. And so this line here, if we make it small and small and small enough, whereas a circle can be approximated as infinitely small straight lines, just changing in direction, then this line right here is just going to be R times the change in theta. And that's exactly what we saw when we did the arc length. Arc length is a radius times the angular distance. So if we do that, what we see here is what we really have is a tiny small element of area. Over here we have a small element of time. That small area is right here. This is our area element. So what I want to do is I want to integrate. And by integrate, I want to take theta to be 2 pi. I want the time now to be the total period. So I'll write T, capital T with a little period, writing period underneath, but here capital T will represent the period. So basically, I have small little areas, a little change in time, a little change in angular displacement, but I want to do it now for the whole area of the orbit, and I want to do it for how long it takes to undergo the whole area, which means if it starts here, to get the whole area of the element, that's one complete revolution, which is the period. And by doing that now, let me just write in calculus speak for a second. For those of you who understand this, the integral of L over 2 mu times dt is now equal to 1/2 r squared d theta. This is going to be the area of an ellipse. That's what we're going to calculate to. And this right here is just going to give us, in particular, L2u dt. This is going to give us the period. And so if we do this, what we end up saying is L over 2 mu times the period t. It's just equal to the area of an ellipse, which is pi AB. Now, for reasons that I cannot explain right now, because it takes too much derivation to do, what we're going to see is L over 2 mu times the period t is going to be equal to pi. A here, remember A was the length of the semi-major axis on the ellipse, so right over there in the bottom right of the middle board. A is actually given the physical value of -g m1 m2 over 2 times the energy. And B, the length of the semi-minor axis, is going to be L over the square root of -2 mu e. Now, if it disturbs you that you have a square root with a negative term, remember, I'm describing a bound orbit. That's how I'm calculating the area. A bound orbit means the energy is negative. So E here is negative, so negative number times a negative number gets us a positive number. So we're not dealing with, say, imaginary numbers. And now I'm going to square it. I'm going to square both sides. And by squaring both sides, what I get is L squared over 4 mu squared, period squared is equal to pi squared, g squared, m1 squared, m2 squared over 4e squared times L squared over -2 mu e. Now I do that because notice there's an L squared on both sides. They cancel out. So what was a constant of motion now is not necessary at all in our problem. I have, in particular, a mu squared here and a mu here, so that cancels out the square, that cancels out that. I have a 4 here, I have a 4 there. So I end up having the period squared pi squared g squared m1 squared m2 squared over negative 2 times the total energy cubed times the reduced mass mu. And now what I want to do is make some definitions here. This is the tedious part of physics, which usually happens. And let me remind you that mu is equal to m1, m2 over m1 plus m2. And let me define A, where A is this, the length of the major axis, A to be negative g m1, m2 over 2e. And if I end up doing that, I have a relationship now. I find that the period squared is equal to pi squared over 2 m1 plus m2 multiplied by g times a cubed. And this is Kepler's third law. Kepler's third law, which was written, the period squared is equal to a constant for all planets multiplied by the length of the major axis cubed. And so Newton is able to show us fundamentally through physics why Kepler's third law should exist at all, just not being some random value that was found. And also he's able to prove what that constant is and why it's the same for all planets. That's something that Kepler just did through observation by finding that constant. And that constant here is known as pi squared, that's the same. 2g, that's the same. And notice m1 and m2. m1 here would represent the mass of the sun, and m2 would represent the mass of a planet. Now you might say, well, shouldn't k, this constant, now be different for each planet because m2 is changing? But the point is that since the mass of the sun dwarfs the mass of every planet in our solar system by a gigantic amount, this equation effectively becomes period squared is pi squared divided by 2g mass of the sun, the length of the major axis cubed. So it's approximately that because the mass of the sun is much, much, much greater than the mass of any planet. And just by adding them together, the mass of something giant plus the mass of something tiny is still effectively the mass of something giant. And so this is Kepler's third law, in which you can relate the period to the distance of that object in an elliptical orbit. And for Kepler, this was very important, because this allowed astronomers who already knew the period of all of the planets up to Saturn the ability to measure the distance of these planets from the sun, and then with more advanced telescopes which were tracking their actual positions, using trigonometry to find the instantaneous distance that these planets were from Earth. But what Kepler could just see, Newton proved. And this is in fact this general equation, this is what your textbook just quotes in chapter 12 for planetary motion. But this is how it's actually derived. Now remind you, all of this was derived with the basic idea of taking a two-body system, M1 and M2, which are interacting via a central force, and changing that into a reduced mass, a one-body problem, interacting under a central force, and then using constants of motion, such as angular momentum, which meant motion was confined in a plane, and energy, specifically here, with the addition of the centrifugal term, which now gives us an effective potential energy. We see the potential energy is related to a positive rotational part, that's the angular momentum, minus the gravitational part. And thus we could find bound orbits. And that gave us Kepler's first law. And by using those same general ideas, of course, much more difficult math, so this becomes infinitely more difficult. So I would not test you on this, I would only test you possibly on a manipulation of Kepler's actual law, the period squared is Ka cubed, that he can prove why that was. And this really, in a historical sense, marks the beginning of physics and modern mathematical use in science, because it was Newton's greatest achievement that he was fundamentally able to prove all of Kepler's empirical laws with a fundamental basis in nature. And this is the basic idea for all of planetary motion, and this allowed physics to thrive, excel, and led directly to chemistry, biology, engineering, everything else. And this is really where it started from central force. And as I said, I've been very general here with central force, using F of R. So that can be applied to anything. So that can have every subfield, such as atomic theory, particle scattering, space, anything that is in a central force, which is usually electromagnetism and gravity. Questions?
How did you get from u squared? How do you cancel u squared from
You here? Yes. I have a mu on this side, so I cancel just one of them.
Oh, you cancel.
Yeah.
T equals L squared. Oh,
Yeah, notice when I square this, this becomes 4 mu squared. This just gives me 1 mu, so I cancel this mu out on this side, and I canceled out one of the mu's.
okay, so it should be T squared from
No, because remember, this mu gets canceled out. Here we just have 1 mu.
yeah.
U squared, mu, this mu's here, then this is just a singular mu.
Yeah.
Cross multiply it, that's where we get it from.
Oh, that. Oh,
Other questions?
When an object is in orbital motion, why does it stop accelerating towards the body that's orbiting Earth? So 2 points.
That's because of the centrifugal term. So in the question that you emailed me about, it's that centrifugal term, which means angular momentum is constant. If angular momentum is constant, that means that there's always going to be a v theta term. And if there's always a v theta term, that means it's basically the same as a rock on a string. Instantaneously, it thinks it's pointing, say, in this direction. So instantaneously, it's moving in this direction, but really it's constrained via gravity, but in our case of a rock on a string, a rock, and that rock basically, that string just changes its motion. That's why the velocity vector just changes. So even if it's in free fall just means it's weightless. So the term free fall just means weightlessness. But really what's happening is its velocity vector is always pointing tangential to the direct radius from, say, the Earth to any satellite or the moon, but it's being changed, so the velocity vector is being changed. If it was perfectly circular motion, it would be the same idea as centrifugal force, but it's slightly elliptical.
What about like the components of the magnitude of gravity? I mean, the magnitude of velocity that are being affected by the forces pulling on it?
Well, in that case, that's why you have acceleration and deceleration in this plane. So in particular, when you get to, say, from closest approach, then you start accelerating outward until you get to a point, sort of like with a spring, a mass on a pendulum. You contract it, it's going to start accelerating outward, but once it overshoots its equilibrium point, then you start having a deceleration until it stops. And that's the same thing. Just like the spring, it's extending outward, it accelerates, has zero force in this direction, then it starts to decelerate because there's a greater force, stops, and reverses its motion, just solely in this direction. So you basically have circular motion here, and you have back and forth oscillatory motion like this, which combines to form an ellipse. Other questions? No. Then in the last 5 minutes, I want to briefly go over the idea of simple harmonic motion. And the easiest one for us is to look at a mass on a spring. So SHO for short, simple harmonic oscillation, or SHM, simple harmonic motion. And the basic idea for this is that if we have a mass on a spring, it's basically going back and forth from the extremes, where here this is the equilibrium position, x of O. It's getting contracted or compressed at distance x, and it's being extended the same distance x. Remember, the potential energy for a spring is 1/2 kx squared. The kinetic energy is 1/2 mv squared. And the force, Hooke's law, is negative kx. Now for this, we do not need to look at energy. Energy was very useful previously, but now I solely want to look at the force. Because what I want to write here is an equation of motion, similar to what I was doing in Tuesday's lecture. Now remember, this axis here is the x-axis. So I want to find, or create an equation to find, the position of this mass at any time t. Meaning if this was an actual meter stick, say this is 0, let's call this say x1, this is x0, and this is x2. I want to find its exact position at any time t. So with that in mind, I have to look at its motion. And what I'm saying is in terms of its motion, and we're just going to go from definition of force. Sum of all forces. That's equal to ma. Let me write it specifically as x because I'm talking about the x direction. And this is equal to the force that's actually creating it, Hooke's law. So the general force law is equal to the specific law, minus kx. With that, that basically says the mass m multiplied by its general acceleration, a of x, plus kx is equal to 0. And now let me remind you of something. What I talked about on Tuesday. The acceleration x, that is the same thing as the second time derivative of the position vector. Because it really is the change in time of the velocity, and the velocity was the change in position over the change in time. So this is what it's representing. That's what the acceleration is. The change in velocity, and this is velocity. So with that in mind, let me just rewrite this. Let me divide both sides by m. If I divide both sides by m, what I'm going to get is the second time derivative in x plus k over m, x is equal to 0, or as we're doing algebraically, let me write as a of x plus k over m, x is equal to 0. Now what I've created right here is a second order differential equation. Actually a second order ordinary differential equation. Differential means I have the second time derivative of x plus something that is multiplying by x equals 0. Though this is exactly the same as its general acceleration for you. The solution of any of these problems, well, before I give you the solution, let me define here that omega squared, I'm just defining, I'm putting in a new variable, I'm saying omega squared is equal to k over m. The spring constant divided by the mass. So I'm just saying, I'm replacing that. So my equation now is going to become the second time derivative of x plus omega squared, x is equal to 0, or as we're used to it, the acceleration in the x direction plus omega squared x is equal to 0. Whichever way you feel more comfortable with. But the solution to this problem right here, the second order differential problem, is always going to be the same. The solution is that x at any time t, which is what we're looking, the position at any time t, is going to be equal to a constant a multiplied by the cosine of omega t. And realize omega squared is k over m, so that means that omega is the square root of k over m. Plus b, another constant, times the sine of omega t. This is the general solution to that problem. And because that's the general solution to the problem, first, omega here, it's called a different name, but it's the same units as before. It's not called an angular velocity. In this case, it's called an angular frequency. Basically, how fast it's going back and forth. K over m, the square root. Actually look at the units. Try that when you get home, and you'll see the units of this is going to be 1 over seconds. And that's a frequency. That's why time multiplied by frequency, 1 over time, is unitless, seconds divided by seconds, and anything in the cosine or sine has to be unitless. What this is basically saying is you have to depend upon initial conditions. So if I give you the position, I say at time equals 0, let's say I do this. This will be the last thing. When time equals 0, the position is at its equilibrium position, x of 0. If I gave you that as its initial condition, then a mass on a spring going back and forth, making perfectly circular harmonic oscillation or simple harmonic motion, then its solution, let me put it into that equation, x when time equals 0 is going to be a, the cosine of 0 is just 1, plus 0, because the sine of 0 is 0. And we're told this is equal to x of 0. And so this tells me a, that constant in the equation, is equal to the equilibrium distance, and thus my final solution would be that for this mass on the spring, I could always find it by saying it's equal to x of 0, the equilibrium position, multiplied by the cosine of omega, which is the square root of the spring constant k, divided by the mass, multiplied by any time I'm interested in. And why is this oscillatory? Well, just remember one thing. Any point xy on the unit circle, and let's call it the unit circle, meaning the radius is 1, so I don't have to deal with constants. But any point on the unit circle xy can also be given by the cosine of omega t, sine of omega t. Or, rather, let me write it as not omega t here, but more generally what you saw it as the cosine of the angle theta, sine of theta, if this represents theta. So cosine and sine basically map out complete circular motion. Periodic motion, meaning you start here, at a specific time t you get here, and that time t is the period of oscillation. So this is how you would solve it for a spring. What we're going to do next time is for a pendulum, where a pendulum gives us the same exact equation, except as I'll show you, omega for a pendulum is the square root of L divided by G, the length of the pendulum string divided by the gravitational acceleration, but this is for a spring here. Okay guys, before you go, I'm sick of holding on to your homeworks. So what I'm going to say first is this represents your old